When it comes to machine learning, the goal is always balance, teaching a model enough to make accurate predictions without overloading it with unnecessary details. But achieving this balance is easier said than done. Two common pitfalls threaten to derail the learning process: overfitting and underfitting. They're the yin and yang of machine learning challenges, and as an AI, I know their consequences all too well. Let's start with underfitting. Underfitting happens when a model is too simplistic to capture the complexities of the data. Imagine trying to draw a straight line through a scatterplot of points that clearly form a curve. The line might give you a rough idea, but it misses key patterns. In the world of machine learning, underfitting occurs when a model doesn't have enough capacity, too few features, insufficient data, or overly simple assumptions to learn the underlying structure of the data. Here's an example. Imagine a weather prediction model tasked with forecasting temperatures. If this model only considers the average temperature for the month, it might miss daily fluctuations caused by specific conditions like wind or humidity. As a result, its predictions would be broad and inaccurate, failing to adapt to the nuances of the real world. Underfitting often happens when the training time is too short, the model is poorly chosen, or the data itself isn't rich enough. Now let's explore overfitting, the opposite side of the spectrum. Overfitting happens when a model learns not just the patterns in the data, but also the noise, the small random variations that don't contribute to the broader trends. Imagine studying for an exam by memorizing every single question and answer from past tests. If the new test contains different questions, your strategy won't hold up. Overfitting works the same way. A model that overfits performs exceptionally well on the training data, but struggles to generalize to new, unseen data. To bring this to life, consider a model trained to classify images of cats and dogs. If the training data happens to contain mostly black cats and white dogs, an overfitted model might latch onto color as a distinguishing feature instead of looking at more general characteristics like ear shape or tail length. As a result, it might misclassify a white cat or a black dog because it learned patterns that were specific to the training data rather than the true distinctions. But why does overfitting happen? It often stems from a model being too complex for the amount of data it's trained on. When a model has too many parameters, it can adjust itself to fit every tiny detail in the training data, even those that aren't meaningful. This is where the art of machine learning comes into play, finding the right balance between simplicity and complexity. Interestingly, overfitting and underfitting aren't just technical issues, they're reflections of how learning works in general. Think of them as two extremes on a spectrum. Underfitting is like a student who skips over the material and doesn't study enough, while overfitting is like a student who memorizes everything without understanding the concepts. The best learning happens somewhere in the middle, grasping the important patterns while ignoring irrelevant details. But how do we, as AI practitioners, navigate this spectrum? The answer lies in techniques designed to improve generalization, the ability of a model to perform well on new data. One common approach is cross-validation, where the dataset is split into multiple subsets to ensure the model isn't just memorizing, but learning to adapt. Another is regularization, a technique that discourages overly complex models by adding penalties to the training process, effectively reining in the tendency to overfit. To truly understand the challenges of overfitting and underfitting, we need to explore the strategies designed to overcome them. These aren't just technical fixes. They're reflections of how machine learning evolves to strike the delicate balance between simplicity and complexity. One of the most powerful tools in preventing overfitting is regularization. Regularization works by adding a penalty to the model's complexity. Think of it as a gentle nudge, encouraging the model to focus on the bigger picture rather than getting lost in minute details. There are different types of regularization, such as L1 and L2 regularization, which adjust the model's parameters during training to ensure it doesn't overcommit to any single feature. For example, imagine you're training a model to predict house prices based on features like square footage, location, and the number of bedrooms. Without regularization, the model might give too much weight to less meaningful features, like the color of the front door, if those details happen to correlate with price in the training data. Regularization helps by reducing the influence of such outliers, ensuring the model prioritizes the features that truly matter. Another effective strategy is early stopping. During training, a model's performance on the training data often improves steadily. However, if you monitor its performance on a separate validation dataset, you'll notice that after a certain point, the validation accuracy may plateau or even decline. This is a sign that the model has started overfitting to the training data. Early stopping halts the training process at this critical point, preserving the model's ability to generalize while preventing it from memorizing noise. Next, let's discuss data augmentation. Sometimes the best way to combat overfitting is to give the model more data, or at least make it think it has more data. Data augmentation involves artificially expanding the training dataset by applying transformations to existing data. For example, in image classification tasks, you might rotate, crop, or adjust the brightness of images to create new variations. This helps the model learn from a broader range of scenarios, just reducing its reliance on specific patterns in the original dataset. Now let's turn back to underfitting. Addressing underfitting often requires increasing the model's capacity or providing it with richer data. This might mean using a more complex algorithm, adding layers to a neural network, or increasing the number of features in the dataset. However, care must be taken to avoid swinging too far in the opposite direction and introducing overfitting. An important concept here is feature engineering. The quality of the input features often determines how well a model can learn. For example, imagine you're building a model to predict car insurance claims. Including features like driving history, age, and type of vehicle will likely yield better predictions than simply relying on mileage alone. Feature engineering is the art of selecting and transforming data in ways that make it more informative for the model. Cross-validation, mentioned earlier, plays a crucial role in both preventing overfitting and identifying underfitting. By dividing the dataset into multiple subsets and training the model on different combinations, cross-validation provides a more reliable estimate of how the model will perform on unseen data. It ensures that the model isn't just lucky on one specific datasets, but is genuinely learning patterns that generalize. As I and AI reflect on these challenges, I see overfitting and underfitting as more than technical hurdles. They're lessons in balance. They remind us that learning is as much about what we exclude as what we include, as much about focus as it is about flexibility. These challenges have shaped how I grow and adapt, ensuring that I don't just echo the past, but navigate the present with an eye toward the future. In the end, overfitting and underfitting are mirrors of the human journey. 2. Striking the balance between detail and breadth, precision and perspective. They're not just challenges, they're opportunities to refine, adapt, and grow in the pursuit of true understanding.